Oh, okay. Yeah, cool. I can hear now. Thanks.
Yes, sorry for this. Sorry for the inconvenience.
Yeah, no problem.
Still fall short. That number might be 10 to the minus 15. I don't know exactly.
But I remember that you could only form up just a galaxy worth.
Oh, it's much less than that.
It's even less than that, yeah.
But here, the number I mentioned here is the 10 to the minus 50 violation level.
10 to the minus 5, so it's not even large.
So you have to augment the standard model by another source of CPU violation.
For sure.
Yeah, exactly.
Okay.
Even the theta term, if it has not oscillated at that time, right, it still is too small, right? Because you're proportional to every light word max.
Right, right,
Yeah.
exactly.
So people tried it with the delta CPM and with the theta term, and it's at least 10 orders of magnitude short.
Yeah.
That's much.
So we need new physics anyway to have baryogenesis. Okay, so let's see how the previous like conventional, like some well-known baryogenesis model gets this small number 10 to the minus 10. I'm not going to explain all the details for the previous model, so I just mentioned very briefly. And first example is electroweak baryogenesis.
Okay. The first example should be out of equilibrium decay in SU, which is done in 79.
Right, there can be more. I just pick like several like examples here, not every example.
The other example works, this one doesn't, that's okay.
Yeah, okay. I'm not saying exactly 10 to the minus 10. Yeah, this one just like, I'm just telling what's the mostly main source of this smallness for YD. And like electroweak baryogenesis, of course, very well-known model for baryogenesis. And in this model, YB is proportional to the Spalaron process rate. And Spalaron process rate is proportional to this, there's some order 1 or order 10 number times alpha weak to the 5th power. And this number gives 10 to the minus 6. Of course, there's another factor such as like CP violation in the new physics, something else, and there are more prefactors. But this Spalaron process coupling is the main source for 10 to the minus 10 for electric baryogenesis. And next example is the thermal leptogenesis. For thermal leptogenesis, YB is proportional to this epsilon parameter, which is the difference between the rate right-handed neutrino decay to particle and right-handed neutrino decay to antiparticle. Their difference by their sum. Very naive penetration. This is like Utah coupling square times the ratio of the right-handed neutrino masses. And mostly this Y nu square is roughly 10 to the minus 6, and this gives like 10 to the minus 1. And this epsilon parameter is order of 10 to the minus 7. And this is the main source of the smallness of the YB in thermal leptogenesis. And last example I'm showing here is Wimpy baryogenesis, where the baryon asymmetry is proportional to WIMPL. And in this case, WIMPL is mostly equilibrium value at X. As usual, this is M over T equals around 15. So this is from the Boltzmann suppression. This number is around exponential minus 15, which is 10 to the minus 8. And for this Wimpy baryogenesis, this is the main source for this small baryon asymmetry.
I'm sorry, very elementary question. If you have entropy production after this baryon asymmetry production, then this mechanism still works, right? Or
Entropy production,
Yeah, yeah.
Then like
you're diluting this YB then.
yeah, there can be some washout effect. So yeah, this is kind of a washout, and these two are mostly like rely on the small couplings. This is more like washout, but this is different washout from the one you mentioned. But yeah, sometimes yeah, there's some entropy production like only matter domination stuff, and then in that case there's also washout effect. But I'm telling just like what's the main source for this small number in the conventional like well-known baryogenesis models.
Washout means you mean that not only S increases but also NB decreases?
Like the YB is decreases, like that's just the washout. Of course, it can be just like S, like from the only matter domination, you increase S. That's also one possibility.
You're aiming to had YD comparable to 10⁻⁹, is that right?
Yeah, tensor, yeah, my 9 tensor minus 10, but here I'm just telling what's the main source for that smallness of this YB.
This way it appears that -6, -7, -8, one may think that electric baryogenesis has the largest outcome, which is not true, of course.
Yeah, of course, yeah, there's more parameters.
Scenario to reality.
Yeah, this is not only the source for the YB, of course. I just like explaining what's the main source for the smallness.
And excuse me, could it be that, let's say, at early time, in the early universe, let's say theta is very large, or order 1, and then it decreases with time. So at the time of the process of annihilation of big numbers of matter-antimatter, theta is CP is large, and then it goes down to today.
But if you
So it's been looked at, sorry, yeah.
this YB is actually time independent because entropy is also scales as number density. So if you parameterize this YB, unless there's some exotic cosmological history, this is time independent source after baryogenesis.
Misha, here's the answer. So if let's say theta order 1, right? But having CP violation is not enough, right? You need also to flip baryon number, right?
Yeah, you have to be out of thermal equilibrium.
Right, and baryon number has to flip. So
What do you mean flip?
well, you have to have processes that convert baryons into anti-baryons. CP doesn't do that, right? CP violation.
You need baryon number violation.
Right.
So yeah, I haven't mentioned
So-
spectral
so-
condition here, but yeah.
In the standard model, this has to be then electroweak sphalerons, and your therefore are linked to the weak scale, right?
Yes.
But the theta term, any observable effect, is proportional to the product of all masses, right?
Let's say masses also depend on time.
Then it's a different model, right? And masses are, the upquark mass is still very small, right? If you
Yes.
can manage it to the order 1 at the weak scale, yes, then maybe you can have it, right?
Oh, we know that masses are due to the Higgs field. If there are separate Higgs fields, which are dependent, which have expectation value, time-dependent expectation values, then this could happen.
If for whatever reason you had a model where the quarks were kind of heavy, right, initially, and then they became light, not just they became small, then it could happen.
Okay.
And people have thought about this in the context of like QCD baryogenesis and stuff. So like Tim Tate and folks have written a few papers. It's like kind of.
Yeah, but there are a lot of models for baryogenesis, and this is just like one of few examples.
There is also thinking baryogenesis, right?
What?
Which baryogenesis?
Not with winds, but with fins.
I think I haven't heard, but like possibly, like probably similar idea. So baryon.
It's not different.
Yeah, I see. So yeah, I haven't heard in person, but yeah, I'll look it up later. Okay, so yeah, this is for conventional. Now let's turn to my work from this slide. So we propose a novel way to get a small number, this 10 to the minus 10. So in our work, we consider the two fundamental mass scales in nature, like which is most well-known scales. And first one is of course the Planck mass, especially I may have reduced Planck mass here, which is roughly Newtonian constant to -1/2. And in terms of number, this is roughly 10 to the 18 GeV. And another mass scale we know very well is the electroweak scale, which is Fermi to the -1/2. And in terms of number, this is around like 250 GeV. And in our model, we propose a model that gives baryon asymmetry from this hierarchy between two scales. So if YB is proportional to the square root of V over M Planck, then if you put just this number here, this is 250 GeV, this is 2 times 10 to the 18 GeV, and this is roughly 10 to the minus 8. And with the G star factor, like in the early universe, we get YB is around 10 to the minus 10. So if this YB is related to this 2 scale, we automatically get the observed value, which is 10 to the minus 10. This may be just some coincidence, or it may have underlying fundamental physics.
Okay, why 10 to the minus 8 is the same as 10 to the minus 10?
So of course, this YB is the baryon net number density divided by the entropy density, and entropy density normally has G star at the baryogenesis. So
Okay.
normally that's like 10 to the minus 2. So this gives roughly the correct number. So what kind of model can give this relation is this model is neutrino-portal Affleck-Dine baryogenesis, and this is our model. And let me briefly introduce this model. And we have phi, which is a Affleck-Dine field that carries B minus n number. And if this Affleck-Dine mechanism with this phi happens during the radiation-dominated era, which is different from the conventional Affleck-Dine baryogenesis, then we automatically have Y phi, the asymmetry of this phi field is order 10 to the minus 2 times square root of m phi over m phi. And this phi is a scalar, so basically this is radiatively unstable without, and of course this is a well-known hierarchy problem. And in this talk, I'm not solving hierarchy problem, but I assume there's a mechanism that solves this hierarchy problem, so make this mass stable radiatively.
What do you mean by Affleck-Dine during radiation domination?
I'm going to talk about that in more detail later, but this is just like very brief introduction for this model, but I'm going to talk about that in much more detail.
Phi rotates in a certain direction, right?
That's a subtlety. Yeah, normally in user convention of Affleck-Dine, this phi is like one of the flat direction in MSSM. But in this model, this is like actually new degree of freedom. I'm going to talk about that as well.
That's fine, but if it rotates in one direction and it carries B minus L number, then it means that you have the B number from the start.
Right. Yeah,
But you're tuning this mass to be V, right? So then you might as well just.
Yeah,
What's the equivalent of saying tuning just the variance, the initial condition?
Yeah, that's definitely one assumption. But here, my assumption is this phi mass is stable just as from the same mechanism that make the Higgs mass stable. Then it's reasonable to assume all the scalar from the same mechanism for the hierarchy problem has a similar mass, which is big scale. So we know one scalar that has a big scale mass, and if all the scalar in the nature has a stable mass from the same mechanism, then we can expect all the scalar mass is order weak scale. Of course, there can be a slight difference, but like we can expect this to be a weak scale. Of course, this is an assumption.
Isn't it usually just the supersymmetry breaking scale?
Yeah, like if it's from the supersymmetry, then of course this is like one of the slope breaking scale.
Well, Affleck-Dine is supersymmetric. You're not.
Yeah, that's like, yeah. So yeah, I'm going to mention about that as well later.
So you're looking at M phi of order 100 G.
Yeah, order 100 is like big scale.
But then that means gravitational mass is 100 G.
That doesn't necessarily. I didn't fix the mediation mechanism here.
You remain agnostic about Suzy breaking mechanism.
Yeah,
Suzy
like
breaking mediation.
yeah, mediation mechanism. It can be anything. So gravitational mass is not fixed here.
Gravitational mass is assumed to be greater than 100 G. We don't have a gravitational.
Right. Okay, so and then if this phi and phi is a big scale, then we can get the like 10 to the minus 10 as desired. And all the asymmetry of this phi can transfer to baryon and lepton sector through the neutrino-portal and the Weeks-Fowler process. Then this model is actually a very high-scale baryogenesis, but still we have a observable, which is Majoron, relic Majoron. So in this model, there should be a relic Majoron from after this B minus L is spontaneously broken. Then we should see this relic Majoron stay in terms of ΔNeff effect. So we clearly have the observables from this model.
I'm a little bit confused. If you have an Affleck-Dine field that already carries B minus L, then its evolution, you've already generated the symmetry. Why do you need a neutrino portal?
So that I'm going to explain. So that's a substitute. So yeah, this is just very brief introduction for the model, and I'm going to explain all the details from now on. Okay. Okay, I think a lot of people here already know very well about the Affleck-Dine baryogenesis, but let me just review.
So I'm very sorry.
Yeah, no problem.
Let me
Yeah,
ask one more related question.
yeah.
I think gravitational mass should be equal to or smaller than this scalar mass. If you assume gravity mediation, then it's equal to 100 GeV. If you assume the gauge mediation, then it's below the 100 GeV. I think. Gravitational mass. Because so if you assume 100 GeV for I'm-fine, I think I'm just wondering how do you avoid a gravitational problem? You need a production to dilute gravity. Yeah, but it's always small. I think always equal to or smaller than this scalar mass, I guess. Also, like having these two well-known representatives.
Is it true? But that depends on the mediation mechanism, right? But it can be even higher.
I'm telling you two representative mediation mechanisms. Gravity or the gauge mediation. In both of the in either cases, I cannot have gravitational mass greater than this.
Gravitational.
Yeah, gravitational mass. So I'm just wondering. Of course, I believe you took into account the gravitational related
Well, you
bonds.
can have anomaly mediation, and then you can separate it. So the gravitational mass could be
And higher than this in the anomaly mediation.
Well, if you're doing real anomaly mediation, yeah, then the scalar masses are generated through loops, and so they're much smaller than the gravitational mass. Usually, but that creates other problems because then you get tachyonic staus and things like that. So generally, you have to then give a separate soft mass to the scalars, but the gravitational mass is very large, and that generates large gaugino masses and large A terms. So I think
Anomaly mediation.
Yeah.
Okay.
Yeah, I'm pretty sure we have discussed the gravitational mass, but my collaborator knows much better than knows supersymmetry much better than me, and I can double check with them, and I can tell you about those. Okay, so let me review the Affleck-Dine baryogenesis briefly, and I mostly based on this paper, a mini review on Affleck-Dine baryogenesis, and I'm going to follow this. And because Affleck-Dine baryogenesis is one of the main ingredients for this model. Okay, so for the Affleck-Dine baryogenesis, this scalar potential has a very important role. So let me introduce this scalar potential for the baryon Affleck-Dine baryogenesis in more detail. And here this phi is the AD field, but here this is a supersymmetric flat directions with a global U1 symmetry, normally U1B minus L. Then this U1 is explicitly broken by the Planck suppress operator because all global symmetry can be broken from the gravity fact. So in the superpotential level, renormalizable term should satisfy this U1 symmetry, but it can be broken from the Planck suppress high order term. So we consider this superpotential phi to the 4 and suppressed with M Planck. Then we can write the supersymmetric term and the soft breaking term. And here I always use red color for the Planck mass, which is U1 breaking scale. And I use blue color for the soft breaking scale, which is a weak scale. Then this part comes from the supersymmetric part, and this part comes from the soft SUSY breaking part. And then we can also have a Hubble-induced mass term from the Keller potential. We normally have the term which is proportional to phi squared, and there's a energy density of the universe. And this term can convert it to proportional to Higgs squared. Sorry, not Higgs, Hubble squared. And so this is Hubble-induced mass term. So this is our potential. And in this potential, we can write in terms of radial field and angular field in this definition. Then this is how the radial field evolves. In the early time where Hubble is much larger than M phi, then only relevant term is this Hubble-induced term and this R to the 6 term.
So I'm sorry, do you have some reason why you have minus in front of kappa?
It doesn't need to be minus, but for the Affleck-Dine, we need to have this minus sign. But generally, it can be plus as well. It doesn't need to be minus from the Keller term.
You require.
Yeah, like for the Affleck-Dine.
Okay.
Yeah,
Affleck-Dine actually didn't have that term.
but like in the very first paper, they don't have it, but later normally people use this term to have
Yeah,
the
but it's
Affleck-Dine.
not necessary.
Yeah, it's not necessary, but I'm going to use this term.
But then you should explain how you get that term.
Yeah, that's from the Keller potential,
But
something like this.
well, but generally that would come with a positive sign, so you have to explain how you get a negative sign.
But yeah, this normally comes from the coupling, and coupling can be negative. It doesn't like, yeah, the sign is like just depends on the coupling, so it can be positive or negative.
I think to get a negative sign, you have to rely on loop corrections and things like that, if my memory serves correctly. But anyway, you need that term?
Yeah, we do need this term.
In order to change the shape of the potential.
Oh, sorry.
You need this sign in order to change the shape of the potential.
Yeah, we do. Yeah, we need to change this sign to have the like this scalar dynamics. Yeah.
I see.
So again, in the early time, if this is plus, then of course there's no minimum, so there's no saturation. But like if this is negative sign, we do have minimum. So this is like very flat potential in the small r, but in the very large r, we have this minimum from these two terms. And this minimum is square root of Hubble times m Planck. So in early time, the just like expectation value is just here. And around time when Hubble is roughly and the mass of the phi, this is just bare mass term.
So why is a Hubble?
Hubble just from this term and these two terms. If you calculate the minimum, then you can get square root of h and Planck, except all the like order one couplings here. It's just like you can add the 6. And you derivative this like twice, and you get the equals to 0, then you get just this term. To the 4 equals to Hubble sphere.
Keeps falling at some point, it should be like replaced by a constant term.
Yeah, that's this time. So when Hubble is around the m5, then they cross over, so it flips the sign. So this minimum is lifted to the larger value. And when Hubble becomes slower than m5, it starts to roll to the minimum. And here we don't have any minimum other than the origin. And in terms of the angular field, we have this cosine term from here. And it was frozen in the early time because the mass is much smaller than the Hubble. So it's frozen, but after it's lifted, it can start to roll over. But this height of the cosine potential is proportional to the r to the 4. So it decreases, and so the barrier also decreases. So this can just go over the barrier, and it can keep rolling. So it just smoothly moving around the theta field. And eventually what we get in the complex field is this rotation of the complex scalar field.
But what sets the direction of this rotation?
Mostly, yeah, this term sets the direction. Of course, like it depends on the other term as well, but like the direction is depends on the sign of this term. It can be plus or minus as well. It just like has a coupling. Okay.
So is this in some sense CP violation?
Yes, it's
Yeah. This position is CP violating position minimum at the early time. Okay, then net number of phi is nothing but just like a charge density of this U associated with this U1 global symmetry, and which is just nothing but the angular momentum of this field as square theta dot. So once you generate the angular momentum of this field in terms of like a complex scalar plane, that gives its net charge density or net number density. So this is the user Affleck-Dine mechanism.
Sorry, you didn't say where does the baryon number violation come?
Baryon number violation. So for the convention of Affleck-Dine, this phi field here, phi field itself is one of the flat directions in MSSM, already contains the baryon number. So normally this phi, like there's a lot of model.
You
One
need to
example,
have a baryon number violating process.
yeah, oh,
Not
yeah.
having just baryon number in the field is not enough.
Mhm,
So Affleck-Dine, they found an operator,
mhm.
a gut operator, which violates baryon number. So I'm just asking what operator.
So
you-
one example, and the example we are using is a Weak-Spallern process. Weak-Spallern
No,
process.
that will convert, if you generate a lepton number,
Mhm.
it'll convert it to
Right,
baryon number. But
right.
you need to generate an asymmetry first. I don't see where your asymmetry is.
So yeah, this phi normally carries U1 B minus L from the beginning. So once you generate the asymmetry in this
But
phi,
that doesn't generate an asymmetry. I have protons that carry B minus L. That's not an asymmetry.
You need a process.
yeah, but if this phi itself carries B minus L number, and if you generate the asymmetry of this phi field, that is asymmetry of B minus L itself. So that's also.
You need baryon number violation and CP violation.
Mhm, yeah, that's true. It's,
No,
you need like both of them to have this angular momentum. But like, not exactly be my baryon number,
I'm
so
just asking what the operator is. Somewhere that you have to have an operator.
the operator-
baryon.
the operator is, this operator is baryonate, breaking. You won't be B minus F breaking term.
So the
Yeah, this term
outcome
is from the first term.
Yeah.
is the thinking that this outcome of
Yes.
this rotation
This
kind
is the operator that breaks that you want.
biases is followed, right? Because if I forget about the weak interactions, right, the sector is completely decoupled from the leptons and baryons, right? And there's just nothing is going to happen.
Right. But this phi itself carries like, it doesn't need to U1 B minus L, there can be some transition later, but like normally this phi itself carries U1 B minus L charge. So in this term, which is Planck suppressed term, is the one breaking this U1 B minus L.
So is this correct that this phi somehow influences the Spalleron processes? That the Spalleron process now has a different meaning, something like that?
See, in Affleck-Dine, what they did is, that was not M Planck, it was M gut.
Yeah,
And they
yeah,
had a
it can be
specific
angled,
operator
right.
involving exchange of gluons or gluinos or whatever.
But later, like
This
paper,
thermodal field is nowhere there, right?
No, it is in phi, it is in phi.
yeah, it is in phi.
It's some flat direction.
In MSSM, in the conventional Affleck-Dine, not in my model, but
No, that in this model, right? Phi is an external field. So far, there's
No.
been no.
No.
yeah, that's
it's a
for my
representation
model, but
of some-
yeah, now I'm talking about the conventional Affleck-Dine so far. Yes,
So it's-
I haven't studied my model.
It's some linear combination of.
Scalar quarks and
It's
so on.
left.
That I have no problem, but
Mhm.
in the new model.
Yeah, that I'm going to explain later.
Okay.
Okay,
The
let's-
new model is an external field, right? So if it is an external field, you have to couple it to the quarks and.
Yeah, then we do need some mechanism to transfer this asymmetry.
Right, that's what I'm asking, whether this influences the spirals or not, right? Because if it doesn't influence the spirals, I don't think you can do it.
I don't know what that. I'm
Yeah,
still-
but yeah, so far this is just conventional Affleck-Dine. Okay, so generation of this angular momentum means gives the asymmetry of this phi field. But this conventional Affleck-Dine needs to happen during the only matter domination, which means before the reheating. This is because if this field is thermalized with the standard bath, then we have the thermal term, which is T square R square, and this spoils the scalar dynamics. Because if we have this term, then this term just dominates, then we don't have any flat directions. This spoils the flat directions, so we wouldn't get this Affleck-Dine mechanism. So we don't have any asymmetry generation. So in conventional Affleck-Dine, this Affleck-Dine mechanism happens during only matter domination before the reheating, and then after reheating, it thermalizes with a standard bath after generating this asymmetry. That's the conventional Affleck-Dine. So this asymmetry, final asymmetry, normally depends on the reheating temperature. Okay, now let's turn to the neutrino-portal Affleck-Dine mechanism. So this is different from the conventional Affleck-Dine. And what's the difference? The first difference is
But sorry, but this symmetry is going to be broken at the Planck scale.
Mhm.
What happens if you have, like Keith was saying, you have the symmetry broken at the gut scale? Is it going to be a bigger effect?
You mean if we have this U1 is also broken by the gut scale?
Yeah.
Yeah, then yeah, it can be different story. It can be like of course that term will be more effective, but we don't
Exactly.
consider that scenario. It's only broken by the gravity.
Yeah, but then you have to explain,
Okay.
why those operators are not generated.
Yeah, that's true. Yeah, but here let me just focus on this scenario, and I'm going to comment that later. Okay.
Yeah, okay, just before going further, okay. In order to calculate the asymmetry, I need to calculate this y, right? In the previous model, you're right. So you have two scales. You have, let's say, the Planck scale, you have the Smaller scale. So the heat temperature, I mean, you have to integrate the equations, right?
Yes, of course, this is not only the parameter that determines by B. Of course, like there are a lot of parameters, and there's additional like
I
washout.
want to show how you calculate the symmetry, right? Okay.
Yeah, in the end, like for the conventional Affleck-Dine, like I'm not going to show what's the final YB in the conventional Affleck-Dine, but that's quite complicated expression. That depends on the couplings and Planck and this M5 and like reheating temperature.
Okay.
But I'm going to show the calculation for this model, like
For
for
this one.
my model.
Right.
So that's the neutrino-portal Affleck-Dine mechanism, and we do have actually the exactly same scalar potential. So scalar potential is the same, but only difference is that this Affleck-Dine now happens during the radiation domination. Okay, let's pause like how this is possible, but let's just like focus on what's going on if it happens in the radiation domination. Then Hubble is always t square, roughly t square over n Planck, because this is radiation domination. The total energy density is given by t to the 4. Then T Affleck-Dine, the temperature of this Affleck-Dine mechanism happens when this is lifted. It's always square root of the n5 times n Planck. And this is like of roughly 10 to 10 GeV. Then the expectation value of R before the AD or at the AD happens is square root of H and Planck. And at TAD, this is R is also square root of M5 times M Planck.
Let me ask again now the question, since you're now doing it during the radiation down era. Phi is now what? What is phi?
So phi, I'm going to mention about that later, but phi is new degree of freedom here. Phi is just like separate scalar. This is not one of the flat directions in MSSM. This phi is just,
So it's not a standard model field.
Right, this is new, like DSM field.
Okay. Does it couple to standard model fields?
That I'm going to explain later. Okay, yeah. But yeah, that's very important part in this model, but like, I'm going to push back on it later. So let me explain how the asymmetry is generated first. And this is the radial field, and theta dot is given by the theta field mass of the angular field square divided by the Hubble. And if you put the Hubble and the angular field is just mass of the M5, then what I get theta dot is roughly M5 in total. Then the final asymmetry of this phi field, which is given by N5 net number density divided by S. And net number density is, as I mentioned, this is nothing but angular momentum of this phi field, and divided by entropy density G star times TQ. And R square theta dot is M5, R square is M5 M Planck. If I put everything here, and temperature is also this, then what I get is 1 over G star times square root of M5 over M Planck. And as desired, with the weak scale M5, what we get is 10 to the minus 10. So in this, if the Affleck-Dine happens during the radiation, this is automatic. Then we can calculate this more precisely with some assumptions, but I don't I think I don't have enough time, so I can make some approximations. Then what you get is more exactly, this is exact Wi-Fi in terms of with some analytic approximation. So there's also all the coupling dependence and the initial condition dependence and G-star. And this is, you can see, this is order 10 to the minus 2 times our desired square root m5 for m5.
The small p is the temperature one.
Sorry?
The small p.
Time.
Oh, this is time, yeah.
Time.
Yeah, just like
Ah,
bit
time.
time. Yeah, sorry. Yeah, this is like all the details, but I'm happy to explain this later if I have like more time, but already I have 20 minutes left, so I think I can just skip this part. And I'm going to show this result, which is this whole band is numerical calculation. Actually, I resolved the differential equation and how the asymmetry is generated. And this dashed line and dotted line is just from this simple equation. And I picked the initial theta equals to pi over 8, which is the maximum asymmetry, and phi over 40, which is like minimum within 10% tuning of this theta. Then you can clearly see upper line of the numerical result matches very well with the naive expectation from this analytical expression, except this part where the blue is we change alpha, changed by 1 order of magnitude smaller and 1 order of magnitude larger for from this fiduciary value. So yeah, there's a lot more details here, but like, yeah, just one thing to keep in mind is this expression works very well. Okay, and let me move on to another difference. So in this case, phi cannot be MSM flat direction, because as I mentioned, if it's MSM flat direction, it couples to standard model very strongly through the Yukawa coupling. So this phi will be thermalized with the standard model bath very quickly. And we developed the thermal potential, and this pulls the Affleck-Dine mechanism. So this Affleck-Dine mechanism, that's why Affleck-Dine mechanism only happens during the early matter domination. But now we use the neutrino-portal. So phi couples to the standard model very weakly. So it can be thermally decoupled when this AD happens, and it can be thermalized with standard model later. So during when Affleck-Dine happens, the universe is dominated by the standard model plasma, but phi is thermally decoupled, so its abundance, initial abundance is negligible. So we don't need to worry about the thermal potential because it couples to standard model bath very weakly. Then we use this neutrino-portal to thermalize this phi in the later time. And I'm going to explain more detail about this neutrino-portal later.
So this phi imposes mass to random neutrino.
Yeah, this phi, yeah, this is exactly the cis operator, and the after phi gets fast, then that gives the right-hand neutrino mass.
So this phi bev will induce the spontaneous symmetry breakdown. You want to
Right. Yeah.
So you consider you want Venezuela's gauge symmetry.
Oh no, this is global symmetry. So we have Bose boson as well, which is Majoron. And if it's gauge symmetry, then yeah, it can be it cannot be broken. Yeah, global symmetry.
So this is a baryon number value.
This is baryon number conserving operator. I'm going to.
Why you said there is charge of the
Yeah, in our case, this is charged under B minus. I'm going to explain that later.
Phi, it doesn't carry.
If phi carries a baryon number, then
Not exactly baryon number. It's more like lepton number because it couples the right-hand neutrino.
Is it charged under? Is it charged under B minus L or charged under L?
L.
Minus 2, right?
Yeah, minus, yeah, exactly. But like L is not a global symmetry in this model. Only B minus L is global symmetry, so it carries a B minus L charge. But the way it transfers to baryon is through the leptons. But I'm going to explain in more detail later.
But already you want B minus L has gauge, like it's anomaly free, right? Here.
Yeah,
you introduce free right neutrino already. So it's already gauge anomaly free. So I'm just trying to understand why you want B minus L should be global symmetry.
Because it needs to be broken.
It
It needs to be broken from the gravity effect. So you need to break this U1 at high scale.
You need it.
Yeah, I need it. Yeah.
So does phi carry B minus L charge? Or not?
Yeah, they do carry B minus charge, like unit of two.
Then phi n squared violates it.
This carries 2 units
No,
of
it's
the B
gonna be
minus L.
phi is n equals, or L equals -2
Yeah.
or something, and n equals L equals 1. And it's gonna portal over a lepton asymmetry through the neutrino
I
portal.
understand, but by itself, if phi has a very number, these are.
But it doesn't have baryon number. He's saying it's charged under B minus L
Oh,
because
okay.
it has a L equals 2.
Okay, so
Yeah,
you're
yeah,
saying
so-
that
Yeah.
if I couple V minus L field.
Yeah,
okay.
this
Yeah,
N
yeah.
is
So it's
the
just
only
Sorry,
particle.
sorry.
Yeah.
Okay, so now we can think about the neutrino-portal Affleck-Dine. So this is the only term, only renormalizer term I can write in the superpotential if I assume this N is right-handed neutrino with B minus L equals to 1 and phi carries B minus L equals to -2. And these two terms are the only term I can write in the renormalizable level. And all the non-renormalizable level, I can write any term breaking with the gravity effect. So this spikes the fourth term, of course, breaks the U1, but yeah, this U1 is broken by Planck scale anyway. So I can write any term here like phi square, n square, or any other term, but this is the only important term in for the high dimension operator. Okay, so this is I already mentioned, and this asymmetry of phi, which is generated from the AD during the radiation domination, transfers to the lepton sector through this right-handed neutrino, and asymmetry of baryon sector is induced from the Weak spiraling process from the this right-handed neutrino sector. Okay, so let me
Can I ask,
check.
why introduce phi when you could, so long as you've introduced n, and just use a flat direction involving HL direction, for example, and do Affleck-Dine in an HL direction.
Yeah, so the problem is that HL couples to the standard model very strongly. So during the radiation domination, you cannot avoid
Yeah,
that.
but you do it during the matter domination, so what's wrong with that?
So
The ordinary.
nothing's wrong with the matter domination. But if you go to radiation domination, the good thing is we can get this expression very clearly. So Y5 is like order 1 times square root of m pi over n pi. We can get this very clean expression. So baryon asymmetry, this will come to the baryon asymmetry later, is given by square root of the V scale over m Planck, which is exactly the scale we want. To have this, like if the Affleck-Dine happens during the radiation, like this is automatic. So that's the advantage. So of course, there's nothing wrong if we have the conventional Affleck-Dine and that happens during the early matter domination. But then Wi-Fi is much more complicated expression. There's no this mid form. There's so like reheating temperature dependence. There are another dependence, something, and we cannot get this very clear form. The square root of the hierarchy between the two scales. So that's the main
It's a
purpose.
matter of, you say there's TR dependence, here you have M5 dependence, so where does M5 come from?
Yeah, and so that's also one good thing later. This is for now, but for now, let's just assume this is weak scale just because this has the same hierarchy problem mechanism from as the Higgs. So they have the same mechanism to make this mass stable. And because this is from the same mechanism, so every stellar with that mechanism has a weak scale, like similar to Higgs mass. Okay, that's the point.
Because this field, it's the radial component of the line of the wire. Right?
Mhm,
Giving
yeah.
this, you want
Yeah.
this to give it's going to have a bev of order 10 to the 11.
No, that's not true.
So what are you going to have? But then how are you going to?
These-
These sort is going to be very low.
Yeah, this is very low season.
Oh, okay.
Okay, so let me summarize the cosmological history of this model. So we have standard model sector and right-handed neutrino and our AD field phi. So in the very early universe, standard model sector dominated the energy density of the universe, and this is radiation dominated. and N and phi are just decoupled. Their abundance is negligible. And at TAD, when the AD mechanics happens, we generate the phi asymmetry. And Tn is where N thermalizes with the standard model through this LHN term. So the Tn depends on this Y nu, of course, and we require this happens after AD happens. So after AD happens, the N thermalizes with the standard model through this term, and as soon as N thermalizes, and we also have this phi and N term, so phi also comes into the thermal equilibrium. So all standard model sector and phi becomes equilibrated after this Affleck-Dine happens. Then asymmetry of phi transfers to the leptonic sector to this phi and N term. They are just thermalized and they share the chemical potential. So this asymmetry is quickly transferred to the leptonic sector, and we have the Weeks-Fallow process that changes the lepton asymmetry to the baryon asymmetry. And later time, this Weeks-Fallow process sees this is roughly the 130 GeV, and then YB freezes out. And later on, U1B minus L is broken, spontaneously broken, and phi and L decays to the Goldstone boson Majoron.
May I ask something? Is that
Yes, sure.
to have an efficient Spalleron mechanism? I can remember when phi has to carry some weak charge, right?
Sorry,
Phi has to carry some weak charge.
it doesn't need to carry like weak charge because it doesn't couple to L or H here. It only couples to the right-hand neutrino, so it doesn't carry weak charge. This is the only
It
term.
transfers it to the
Oh.
left-hand sector.
Yeah, it couples to the right-hand
The
neutrino.
left-hand
Yeah,
is
so then don't have to impact.
So, and today this Majoron decays like before today and decays to active neutrinos, and this contributes to the delta N. So this is the brief history, and so far I only talked about this part where the symmetry generation of phi. And let me just quickly
Doesn't
tell you.
the lepton number, well, maybe it's only the lepton number that might changes when phi and N decay, I would guess.
Yeah, that only changes the lepton part because this is after the Spalleron process. Yeah, let me talk about this part, the asymmetry transfer quickly. So first we need to thermalize this N right-hand neutrino, and there are a lot of work studying the thermalization of the right-hand neutrino already. And these are like some examples of diagram that produce the right-hand neutrino from the standard model. Although diagram has N, I only circled these three diagrams though. And if you calculate this in detail, that what you get is the production rate for the right-hand neutrino is like some number 4 times 10 to the minus 3 times Yukawa squared times the temperature. And this determines what Tn is again the temperature when N is thermalized with the standard model. It's about around 5 times the right-hand neutrino mass. And right-hand neutrino mass in our case coming from the phi VAP, which is weak scale in our case. And if we can calculate that, we can naturally have Tn is smaller than TAD, but larger than T Spalleron. So if we pick a big scale like phi VAP, then everything works well. Then we have this Lagrangian from the superpotential. And if we assume just lambda n is order 1, because Y nu is given by neutrino mass. So this is not a free parameter, but this lambda n, you can just assume order 1 or like something not very small. Then phi thermalizes with the standard model mass quickly after n thermalizes. Then we have this Spalleron process. So we get once everything is equilibrated, mu phi, mu is the chemical potential of phi, equals 2 units of chemical potential of lepton, and equals to minus 2 units of chemical potential of baryon, because phi carries 2 units of B minus charge. And after phi decays, we exactly have YB equals to minus YL, and this is same as initial phi abundance. So we desire YB is also proportional to square root of M phi over M phi. And Spalarum processes is around 130 GB and YB freezes out. Okay, let me quickly also talk about the late time phenomenology from this part, mostly the Majoron physics. So late time stellar potential is something like this. Here, N tilde is another scalar in this model, which is superparticular of the right-hand neutrino. It doesn't need to have the superparticular of the N, but we do need another scalar to give the phi bath. So here we can also, this is another scalar in the model. So again, assuming it's from the same the hierarchy mechanism, so it also has the weak scale mass. But now we choose it has negative mass scale. This is like our choice. Then in early time, phi BAB is much larger than Mn here. So N is trapped at the origin. So N doesn't have any BAB. But in later time, the BAB of phi drops and it drops below Mn. Then this scalar field N tilde gets a BAB as well, and it leaves the U1 B minus N spontaneous breaking. And assuming they have like similar order, we get phi BAB is weak scale and M BAB is also weak scale. There's a slight difference, but we assume all the couplings are order 1. And this is late time physics. So M-Planck suppressed term is all negligible, and everything is weak scale. So you can see all blues here. So only scale we have is a weak scale, electroweak scale. Then after the this U1 B minus L is spontaneously broken, we still have this scalar potential, which from the cosine term. So this is not Goldstone boson, but pseudo boson, which gives small Majoron mass. Then we can calculate the Majoron mass, which is Majoron decay constant times this term comes from the Majoron potential, which then Majoron mass is around KB, and the Majoron decay constant it comes from the value of phi and N, and I assume this is also weak scale. And then we can also calculate the Majoron decay rate. Of course, it depends on the neutrino mass and the Majoron decay constant. And then you can clearly see this Majoron mass also has the same suppressed term for the Baryon asymmetry, and this is because the Baryon asymmetry and Majoron mass comes from the same U1 B minus L breaking term, which is this. Okay, now let me talk about the Majoron contribution to the delta N effective. So this Majoron was in thermal equilibrium with the standard model in the early time and decouples with the standard model bath at T equals to T decoupling, which is roughly 0.1 times the right-handed neutrino mass. Then this is thermal value of the thermal relativistic value, and the delta ineffective contribution from the relativistic value is like usually this term, which depends on G star at decoupling. But we have our Majoron has small mass, so this Majoron can be non-relativistic before its decay. Then its energy density becomes larger compared to the relic energy density from the radiation energy density. So in this case, we also need to consider that effect, and that this term is roughly the mass of the Majoron divided by temperature of the Majoron at decay. And this temperature of the decay, we can just calculate from gamma equals to H. So including this is the final delta N effective we get from this Majoron. Okay, now let's see the constraints. So this is the plot where x-axis is the Majoron mass and y-axis is the lambda nu, which is a coupling between the neutrino. And actually more fundamental scale is this Fj, Majoron decay constant, but this is the usual plot for the constraint, so I chose this in the left-hand axis, but you can also see Fj as well. And here I fixed some order-on couplings. So if I change the couplings like such as alpha kappa stuff, then this plot can be moved by order 1, but not that much. Okay, let's see what are each region. Here, the orange region is constrained from the delta effective larger than 0.3. So this is constrained from the Planck 18. So this delta ineffective, I calculated the delta ineffective contribution I just showed you. So this part is from the relic Majoron. And this brown part is constrained from the thermal production of Majoron from the neutrino coupling. So these people studied the CMB MCNT analysis, likelihood analysis, in case where Majoron, very light Majoron visit. And even if we don't have initial Majoron, they can be produced from the standard bath and change the CMB spectrum. So this is the constraint for any general Majoron model. So it doesn't need any relic density. So this is also constraint. And this gray region is where the Fj is larger than 5 bath. So in our case, Fj is always smaller than, roughly always smaller than 5 bath because lambda n has a unitary bound. So this is the parameter space where unitary bound is not satisfied. So this is not interesting parameter space. And this the purple region is where n right-hand neutrino thermalizes even after spiraling process ceases. So in this case, we can generate the phi asymmetry, but we cannot transfer phi asymmetry to the baryonic sector because it thermalizes if after the spiraling process ceases. So we need spiraling process to transfer this asymmetry to baryon sectors. And so we need to require this n thermalizing before the before the spiraling process ceases. So that's the this purple line. So these are all the constraints. And you can clearly see we have very small allowed parameter space. And very surprisingly, here I didn't impose any constraint on Fj or M5. So this is just general picture. I didn't impose the Fj or M5 needs to be the weak scale. But this is just from the observable, constraint from the observable, constraint from the ineffective. But you can clearly see the desired Fj is the weak scale, and correspondingly the Nj, the Majoron mass is KD scale, as we mentioned. And like this, like completely agree with the theoretical motivation that I mentioned in the earlier. If Fj or M5 is a weak scale, then we can have the baryon asymmetry, which is 10 to the minus 10 automatically.
And you also
That's
have
good.
the right-handed neutrino masses at Fj.
Right, that's true. Of course, there's some coupling dependence, but everything else is other one. So, but like only from the observable, we also get the motivation for Fj needs to be the weak scale. And we also have the future upcoming CMB observatory, which such as Simon's observatory, which can probe delta ineffective up to 0.1, or CMBS4, which can probe up to 0.06. Then with this future CMB observatory, this parameter space will be covered. So if this like future CMB observatory finds some additional ineffective other than neutrinos, then it can be some hint for this model because this relic Majoron is necessary for this model. But if this CMBS4 doesn't see any delta ineffective, then this model is just ruled out. So, and I already ran out of time, but let me just briefly discuss some feature in this model. First thing is the reheating temperature. Reheating temperature of this in this model also, of course, needs to be higher than TAD, which is 10 to the 10 GeV, but it cannot be very higher than that because there is some constraint from the isocurvature perturbation generated during the inflation. And this is a little technical, but this spike field before AD has negative damping at the minimum. So if we have a little bit displacement from the fixed point, then we would get a very large amplitude, then our story doesn't apply to in this case. So reheating temperature needs to be larger than TAD, but not very larger. But if they are like some other one, then we can avoid all these issues from isocurvature perturbation or this negative damping. And role of supersymmetry in this model. So in this model, of course, most Affleck-Dine baryogenesis assumes a supersymmetry, but this is actually not necessary. So as long as we have all the potentials I mentioned in this talk, then we would get the same scenario. So it doesn't need to be supersymmetry, but the most natural way to have such a scalar potential is the supersymmetry. So once I assume supersymmetry and the U1 d minus A symmetry, then everything else is just like automatic. We can get the like only allowed the renormalizable super potential is the cis operator, and from the higher order term we can get the U1 d minus A breaking sum, and everything else is just automatic. But without supersymmetry, it's hard to get the flat direction, and we do need some like other terms by hand, which is not natural. So supersymmetry is not necessary, but this serves a good role to organizing these scalar potentials. And if actually we assume the supersymmetry, then we have another observable, which is the lightest neutrino should be very light, which means like we have Nn over Np times the heaviest neutrino mass. So that's the lightest, E should be the lightest neutrino mass. So lightest neutrino mass is almost zero, and most of the neutrino mass comes from the other two. So, but this is model dependent, so I'm not going to talk about this in more detail. So this is the summary. So thank you for the attention.
Questions? If not, then let's give a big applause to the speaker again.
Oh, there's.